My name is Ory Segal. I'm going to be talking to you about serverless security now. We're 5 people and we're making noise, so okay. A little bit about myself. I spent the last 20 years dealing with application security, mostly around research, developing products for some of the application security industry leading companies. IBM for IBM AppScan, Sanctum AppShield, Akamai Kona cloud security product. I filed about 20 patents in the field of web security, static analysis and dynamic analysis mostly. I'm a web application security consortium officer, contributor to OWASP, NIST, MITRE, W3C, and so forth. And hopefully we'll spend the last the next 20-something minutes talking about serverless security, and if everything will work properly, you'll see a very cool demo. So in general, just to align a little bit, when we're talking about serverless security, we're actually talking about or referring to application layer security, and the reason is that in serverless, the cloud provider is responsible for securing the infrastructure. So anything from the locations, the physical servers, the data centers, the locks, the guards, the networking, all the way up to the containers and the serverless runtime. All of the security responsibility for that part is handled by the cloud provider, and you are still responsible for securing the application layer. So everything that you see here in blue is still your responsibility when you develop serverless applications. We don't expect this to change anytime soon. Nobody's going to take the responsibility away from you and be responsible for securing custom code that you're developing. So the application layer includes obviously configurations, roles, access management, the code itself, applications that you develop, as well as the client side and the data in the cloud, and data at rest and transit. Just again to sort of align on how an attacker can gain access to your serverless functions, just imagine the very simplistic scenario where you have an event, the event triggers a function, the function does some task that you develop. Usually it will interact with some external resource. This could be a cloud service like an S3 bucket, a DynamoDB, or even a RESTful API on the internet on a remote server. And then it will generate some output. So there are 3 ways in which we see an attacker accessing your serverless function and potentially manipulating the business logic that you developed. The first one is through the event data. And maybe I'll stop for a second and ask how many of you actually deploy serverless applications in the cloud? Okay. So for the rest of us, the event is what triggers the function. The event brings with it data, okay? The data about what happened. If we're talking about an S3 bucket that changed and triggers a function, then the data will include the bucket name, the file name that changed, who changed it, and so forth. If it's an HTTP request, the data will be HTTP headers, query string parameters, body parameters, and so forth. And there are different messages that arrive with each event type. And so an attacker can potentially manipulate these fields in order to inject malicious data into the function. And obviously that only applies to user control fields. Okay, so not all the fields are controlled by the user. Those that are, an attacker can use them to inject malicious data. When we're talking about injecting data, and you'll see that in a second, we're talking about SQL injection, process scripting, remote code execution, and so forth. The other way an attacker can tamper with business logic is through the code itself. And there's a wide range, a wide spectrum of how an attacker can do that. Just think about somebody running a cross-scripting or a phishing attack against one of your employees, gaining the AWS credentials or the cloud credentials, and through that deploy code out of band. That's one option. The other one is for an insider, a disgruntled employee, somebody that still has access to your systems, deploying code outside of the normal CI/CD process. But also through a third-party library. So think about how many open source libraries we're depending on in serverless, especially in serverless, because we're trying to keep the functions small in size. We rely a lot on open source packages, and these packages as you probably noticed in recent months, could become infected, poisoned, typo squatting, all sorts of tricks to get developers to include malicious code. So that's another way in. And last but not least, by compromising one of the components that the serverless function interacts with during execution. So if the serverless function brings data during execution from an S3 bucket or a blob storage, and we have access to that storage or that location, we can eventually infect the function with malicious data. And those are the three main ways an attacker can modify the business logic or try to tamper with the business logic. And what can an attacker actually gain from this? So anything you can think of from the world of application security, from injection-based attacks to bypassing authentication, leaking sensitive data, manipulating business logic, and even denial of service, even though many people think that serverless functions are immune to denial of service, there are concurrency limits, and if you can get the functions to hit the concurrency limits, you can deny other users from using other functions in the account or even that specific function. The question that usually comes at this point is, why can't we use existing application security solutions? And usually that would be a web application firewall, RASP, runtime application self-protection, and even other solutions. And if you look back at traditional application security solutions, you notice that they all require you to deploy something on the network or on the server. If we're talking about a web application firewall, it needs to sit between the end user and your endpoint, your HTTP interface. If we're talking about runtime application self-protection, you need to deploy it. You need to deploy an instrumentation agent on the host to instrument the runtime. If we're talking about additional, more auxiliary, security solutions like IDS, IPS, you need to deploy them on the network. You need sensors on the network and so forth. And in serverless, we're sort of out of luck. The thing is that in serverless, we don't own and we don't have the liberty to install any kind of service like that or agent like that on the serverless environment. The only thing that we control is our own configuration and our own source code. So any kind of solution has to come from within the function itself. And those traditional security solutions are obviously becoming obsolete. Now, just to put it into a diagram, if you take a modern, web app stack for that matter, could be on-prem, in the cloud, hosted. Today, in order to sort of airtight secure it, you deploy a wide range of solutions, starting from next-gen firewall to block inbound traffic or inspect inbound traffic, web security gateway to inspect outbound traffic, EPP on the host to detect malicious behavior, IDS, IPS, and even a web application firewall to inspect layer 7 traffic. When you go serverless, the entire underlying infrastructure is no longer in your control, and you have to give away the ability to deploy these solutions. And in essence, today, when you deploy functions to the cloud, to the public cloud, these functions are sitting, facing the internet, facing the users, and facing the attackers. And the only thing that stands between them and the attacker, or between success and failure, is your ability to write resilient code and to write resilient configurations. Now, from the people who raise their hands that they deploy serverless functions, how many of you have a serverless security strategy in place? Are you doing something actively to secure your functions? One. Okay, so it's not statistics of big numbers here, but you can see that people who have been deploying serverless functions for a few years now are basically going without any kind of security solution and relying on the fact that their logic is resilient. Earlier this year, in January, we published a white paper together with a set of vendors and thought leaders in the industry. It's called the Serverless Security Top 10 Most Common Weaknesses Guide. It's available now free and unbranded at the GitHub repo that you see here. And it includes a set very similar to the OWASP Top 10. And by the way, we are turning this now over to OWASP in a project that's called Cloud Native Top 10, as well as to the CSA, the Cloud Security Alliance. So these are the top 10. We don't have, we only have 30 minutes, and I waited for everyone to join, so we don't have a lot of time. But starting from event function or function event data injection, broken authentication, bad configurations, overprivileged functions, role permissions, inadequate monitoring, obviously insecure third-party dependencies, secret storage, and so forth. We'll see a few examples of a couple of those now at the demo, and it will make everything a bit more clear. Okay. I'll briefly go over automated security testing for serverless. There's not a lot to say here yet, so I'll be very quick. If you're used to using static analysis solutions, then you're again out of luck. The traditional static analysis solution tools sort of concentrated on finding vulnerabilities based on code flow analysis or data flow analysis inside the code. And in serverless, as you probably know, you have an event that is out of your control, triggering a function, and then data gets inserted maybe into some storage, and then from there triggers another function, and following data flow in distributed microservice, disparate architectures like this is very hard. And so traditional static analysis tools are still very useful for detecting vulnerabilities inside a single function. But if you look at or try to detect vulnerabilities as a result of code or data flowing between disparate functions, then there's going to be a problem there. The next type of scanners is dynamic application security testing tools. Again, I haven't seen any tool from the existing set of tools that supports testing or natively testing serverless applications. We at PureSec actually published an open source proxy that allows you to test for SQL injection by using SQL Map, which is a tool that everybody, at least in the application security field, likes to use and allows you to do the testing natively. But I haven't seen any dynamic application security testing tools that still or already concentrate on serverless. And obviously IAST, which is interactive application security testing, where you deploy agents, is again not relevant because you can't deploy agents. So now we'll do the demo. And in the demo, I'm going to, actually, I have another slide. We created a really, I think, realistic application for this. Usually the applications that people hack into are not very believable. And so this is a 100% serverless application. It's an HR application where candidates send email with their CV in PDF form to the HR department. The email passes through the Amazon SES service to an SNS message that triggers a Lambda function. The purpose of the Lambda is to extract the email, extract the attachment, turn the PDF into plain text, run a candidate qualification analysis on the text, put everything inside a Dynamo table that is then exposed to the HR department for inviting people to interviews. Why are you smiling? You have a system like that? Okay. And in parallel sends a response, an email response back to the candidate that the email was received. And let's see it in action. Okay, so in order to interact with the system, we're going to use a very modern interface called email. This is the way we interact with the system, right? We'll send an email to the company. Just a moment. Actually, I have it here. Okay, so I'm going to attach a PDF. And the PDF is going to be my CV. And I don't have any malware in it, as you can see. It's just a normal PDF file. And we'll attach it. And we'll wait a few seconds for the cold start, the dreadful cold start to pass. In the meantime, we can already see in the HR front end that the message was received, and we have all the contents We can invite the person to an interview, and that's pretty much what the system does. You can already see that I got a receipt back. And this is completely live and real, by the way. So now I want to try to attack the application. Any ideas of how I can do that? Okay, so false email with false attributes. Okay, I can use it to reply to another user. That's also an idea. So usually when you try to pen test or attack a web application, you have a lot of, you have forms, and the form has fields, and you can try to tamper with fields and fuzz them and send attacks inside the fields, headers, etc. Here we're working with email. That's our interface, which is a bit problematic from an attacker perspective. It's not very enabling a lot of attack vectors. So first of all, I have obviously to send the email to the same place. The subject doesn't really matter. And then I have to attach the email. And the email is basically, the attachment is basically my only way to somehow manipulate the system. I'm going to copy and paste the original one so you trust that I'm not doing anything, any foul play here. And we're going to try and probe whether the system is vulnerable to command injection through the file name itself, assuming that something upstream inside the system is taking the file, copying it from one directory to another, maybe using it in the call to translate it to a PDF, from PDF to text. So the file name is sort of my only field to try and fuzz and pen test. Now, assuming that the file name is using somewhere inside the file system, using some shell commands, I'm going to guess that I can inject something into the file name itself. And what I'll do is I'll type John, semicolon, sleep 5000. Anyone can guess, like, what am I doing here? Okay, so I'm trying to inject a secondary shell command using semicolon, okay, assuming that this is running inside the shell. And I chose to use sleep because there's not going to be a direct response. It's not like a SQL injection when I send an apostrophe and I get a 500 error back with a stack trace. I have to use some other blindfolded technique, and using time-based attacks is the best way to do that. If the system is going to sleep for 5,000 seconds, I'll know that it's vulnerable. And when Lambda sleeps for 5,000 seconds, it means that it's going to time out because the default is 5 minutes. Just a moment. And so now we have to wait 5,000 seconds for us to understand if it's vulnerable, but you can trust me that it is. And so we won't do that. And the next step of the attack is to try to get the source code of the function, because we're working blind. It's not comfortable to try to hack into a system that you can't reverse engineer. And so we'll use the same command execution to send us the source code of the function back to the email. Just a moment. Since it's going to be very ugly to put that inside the file name of the PDF, I already stored the malicious payload that I want executed on pastebin, so it's very easy to point to it. And all I need to do after the semicolon, instead of calling sleep, calling curl to fetch the data and pipe it to a Python child process. And that's what we'll do in the email. And the way it will look is, okay, so what I'm doing here is the same semicolon that you saw here. I'm defining a shell variable. I'm calling curl silently to fetch the data from pastebin, and then piping it through the standard output to a Python child process. And what this does, if you look again at the source code, it's basically taking the handler itself, opening the file, and dumping it back into the email. That's all it does. It's sending me the email. In the email, it's going to send me the command back, the source code. And the interesting thing is that I crafted the payload in a way that if you actually, the function is going to run normally and do what I asked it to do. You can already see it came back. And if you look in CloudWatch or in CloudTrail, in this case, you won't see any trace that I just licked the source code of the function. The function is still running normally. So obviously the CV was received, and then the source code. I took the liberty of taking the source code earlier and putting it inside Visual Studio Code, so it'll be syntax highlighted. So let's take a look at what the developer is doing here. The developer is creating a Dynamo client. And by the way, the developer wasn't stupid. They used an environment variable to store the table name. It's not hard-coded, but it's very easy for us to reuse that in our malicious code later. They're extracting the SNS message, checking that the file name ends with PDF, another good security practice. So the person wasn't completely clueless, but we actually bypassed that using the hash sign. And then the vulnerability really happens in this point. So the developer is using a binary called, a very common and popular tool called, a CLI tool called PDF to text to transform PDF files into plain text. But they're using the file name that we're sending them inside the command without validating it first. So when we did a semicolon, like this, we are basically adding a secondary command. So two processes are going to run. And this is the main problem. This is the first problem. The second problem is that the developer is using Dynamo put item, which is the API, the Amazon API, to insert data into the DynamoDB table. And if the developer gave the function too much permissions, in theory, the developer should have only given the function put item permission. So we only want the function to always put data into the table. We never want it to read. So this is the table that we want to steal and leak the data from. And let's see how we do that. So again, I created a payload and stored it inside pastebin. And it looks like this. It doesn't do much. It basically just scans the table. And again, I don't need to know the table name. I'm just scanning it and sending everything inside the email. And the way I get this to work is to draft my last email today. And use a very similar payload, this time with a different URL to pastebin. And then in 5 to 10 seconds, you're going to see the world's simplest data leakage attack. It took us 3 emails. Think about a classic SQL injection attack would probably take you a few thousands of requests using an automated tool to extract bit by bit or character by character from the database. In our case, it only took 3 emails. And we relied on 1 vulnerability and 1 misconfiguration. So there it is. That's the entire database leaked via email. So the purpose of the talk is not to scare you, though. I still think that serverless is the best thing that happened since the invention of the wheel. And so let's concentrate on what you can do about this. So we saw the demo. And, okay. 6 takeaways that I hope you already know. The first one is to get your secure serverless CI/CD programming in place. A lot of this has to do with the fact that people push functions out of band, not through normal CI/CD processes, in an insecure manner, don't scan their code, don't validate their packages. So starting with knowing how you deploy and doing it in an orderly fashion is critical to this, the success of everything you're doing. The second one is to gain security visibility. A lot of what you just saw doesn't appear in any kind of logs. So CloudWatch normally wouldn't log these kind of things when data is leaked, when somebody's accessing tables, sensitive tables. That's not the right solution for you. You need to be able to log things properly, use CloudTrail, use tools for serverless visibility. There was just a talk now by Epsagon as well. Obviously follow the least privilege concept, and that is key. That is very important to what you just saw, and people keep talking about it, but until you see it in action, you don't really understand it. In our case, in our demo, the developer should have given the function the ability or the permissions to only put stuff into the table. We exploited the function and we used it to do lateral movement and reach data that we weren't supposed to reach normally. So that could have been entirely remediated if we had strict IAM permissions on the function. And think about it, we had code execution. We could have been left only with the ability to put stuff into the table, never to steal data. And only that would have been possible by using strict or least privilege IAM rules. Obviously, scan any third-party open source dependencies that you're using. Make sure that they're not poisoned. Make sure that they don't have vulnerabilities in them. I'll show you a trick in a second. Follow cloud security best practices. You should check out the AWS blog. The PureSec blog is also there. And deploy a serverless security platform. Come talk to Avi and me after the talk. I'm going to skip that. Since you'll have the presentation, there's a set of open source tools that you can use to help you with the things I talked about. We have a free library that helps developers to make their functions more secure and more robust and resilient to malicious behaviors. It's called Function Shield, and it's completely free. You can use it today, as well as a tool to auto-generate least privilege roles and permissions for AWS functions. So that's it. We are out of time. Thank you.